Hey, so I wanted to do a video on the padding oracle attack. However, when I was writing the blog post about it, I found it to be a little too dense. There was just too much information, and I wanted to go through building the CBC mode block cipher and leaving it vulnerable, and then going on to the attack with all of the math included, and it was just too much, and I found it to not be an effective way to get across what I was trying to get across. So because of that, I decided maybe a video would be better. I don't normally do videos, and I'm not very comfortable in front of a camera, and I'm hoping that'll change as I do this more. However, I thought it would be cool to do some live coding and make a video that way. So the idea I had was I was going to split the videos up into two parts for this. One part being building the CBC mode cipher, and then the next part is building the attack. So hopefully this will be short enough to keep attention, and I don't want it to be too dry and boring, so hopefully the live coding will help keep people interested as well. They can yell at the screen when I make stupid mistakes and point out how the code is crap. I think it's more engaging in that sense. But also they can see how easy it is and how little it takes just to code this stuff up, and that's really my ultimate goal is just to show how easy this stuff can be and how easy it is to leave yourself vulnerable to some of the attacks that are out there. So a quick disclaimer, as always, don't trust the stuff that you write for cryptographic libraries. Always use the libraries that are vetted by professionals and the security community as a whole. You hear the expression, never roll your own. Well, yeah, don't. Play around with it if you want, but yeah, don't trust anything you write. Okay, so now that that's taken care of, I guess I'll just jump into it. So if you're not familiar with block ciphers, that's okay. Just follow along. It won't. You don't need to know any of the details behind block ciphers for this. If you do want to know about AES, which is the block cipher I'm going to be using to build the CBC mode of operation, there's a really cool link that describes how it works in comic form, and it's really awesome. And so I'll post it in the blog post as well as in the YouTube description. But anyway, block ciphers, if you're just going to use it to encrypt data one block at a time, well, these block ciphers have, first off, constraints in that they require a certain size of data to encrypt. For AES, it's 16 bytes. So you take your data 16 bytes at a time and you run it through the cipher. If you do this and you just use the cipher itself and you encrypt using your key and then decrypt, you're using what's called standard mode, or ECB mode, and that stands for electronic codebook, and that's really as simple as it gets. That is the standard block cipher mode of operation, where you take your data. In the case of AES, you take 16 bytes of data, run it through the encryption method, giving your key as well, and then you output your ciphertext, and you do this for however many pieces of data you have, that fit into 16 bytes. And so the problem with this is that if you have patterns in your data, for instance, let's say I have a string of 16 bytes that repeat throughout your data, if you encode this, you're actually going to leak those patterns out. Maybe not intentionally, but it's what's going to happen. And I have a really good picture that shows this happening. Cool. So here we have the Linux Penguin. And if you just run it, if you encrypt it using ECB mode block ciphers, you'll just get this image, which you can quite clearly tell what it is still. And in fact, you still get these diagonal lines through the image where there's white. So it's not a very effective method of hiding your data. Whereas you can see in this third picture, we've got quite a bit of noise, and it's really hard to glance at it and see any kind of pattern at all. So that's what we want. And one of the ways we accomplish this is by using CBC mode, which is it's a mode of operation that involves chaining your output to your input. and the CBC stands for cipher block chaining. And it really does make sense when you look at the picture. We take our plain text and we run it through the encryption method of our block cipher, and we get our ciphertext out, and then we XOR, that's the circle with a plus sign in it, we XOR this with our plain text that's coming next, and then we, by doing that, are adding some entropy to the data, and then we run that through the encryption method with our key, and then we get another ciphertext, and we just keep chaining the output to the plain text by XORing it. And this is where it gets the name cipher block chaining, and it's quite effective. It actually does work really well, but as we'll see soon, it does have the potential to give yourself a vulnerability, which is not good. Oh, and this is encryption, and decryption works kind of like in the reverse. Just you take your ciphertext 16 bytes at a time and you decrypt it, and you'll get some intermediary form of your data, which you need to then XOR with the previous 16 bytes of your ciphertext. This kind of operation sounds a little more confusing when said, and this image does do a good job of explaining it, and I urge you just to ignore the initialization vector for now. But this image does a good job of showing it. However, it can still be kind of confusing. I assure you that when we see the code, it's actually very easy, and it's not hard at all. Quite intuitive. It's actually quite intuitive. So once we code it, you'll see how easy it is. But since we're coding the CBC mode of operation, let's just get started and run through what we need. And so I have a main script that I'm going to use, and we're going to use this to import this AES CBC, which is we're going to create that, and we're just going to be able to initialize it and use it to encrypt data. We can print out how that looks like, and also we can decrypt this, and we should get whatever we encrypted, and that's the goal for this video. And I think it should be pretty intuitive, the process for building it. So I do have one utility function that I've made already, and I'll leave this up, and it's just essentially allowing us to XOR 2 byte vectors together. And I'm using Python 2.7, and as far as I know, there's no really good built-in that does this, so this is fine. Yeah, so this is the only stuff that I've pre-made. Going to the file where I'm going to put the AES CBC code. Well, here I have it as a class, and I'm not going to say whether it's AES 256, 192, or 128, whatever. I'm just going to let us build it generically, and then based on the key size, then it'll be whatever. So to help us, the primitives I'm going to be using come from PyCrypto. If you don't have it, it's pretty easy to get. You can just do pip install PyCrypto, and that should give you the library that you need. And then it's kind of weird. I don't know why you import it using just crypto. I'm not a big fan of inconsistencies like that, but that's how you import from this. And we just grab the AES primitive. Let's see. Oh, also we have this helping function, get random bytes, and all that does is really just what it sounds like. You get some random data, and it uses either dev/urandom if you're on Linux machine or POSIX machines, and if you're on Windows, it uses whatever the Windows equivalent is. I am on Windows right now. I'm normally a Linux user, but I'm on Windows because it has the broadcasting software that I need to make the video. So hopefully I'll be able to do this on Linux someday, but I'll figure it out. Okay, so basically if we're going to get started with this, we want to be able to initialize our CBC object with some kind of key, ideally. And if we don't supply a key, I'm going to go ahead and say I want it to default to some random string that is cryptographically as generated from a C spring, basically. So when I initialize, I want to store the key on the object instance, so we store the key. And then I also want to store an initialized primitive. So in this case, I'm going to call it underscore cipher. And I'm going to do initialization, which for PyCrypto, the AES primitive is initialized just by doing AES.new and then whatever the key is as an argument. So that's pretty easy. And then for this, we're done. As for the interface, I just want two methods really. I want to be able to encrypt my plain text data, and I want to be able to decrypt my ciphertext. Perfect. Okay, now you noticed I have also imported base64, and the reason that is because if I were to just encrypt something and spit out the data, well, if I have some bytes that are control bytes, then that doesn't play so well with terminals. And so the idea I want to basically base64 encode anything that I encrypt and return it, and then on decryption I'll decode whatever's coming in. So yeah, that's why I imported base64. Okay, so focusing on the encryption part first. Well, from what we know in AES, we know that it will work only 16 bytes at a time. So when we call the encrypt function on our primitive, we have to make sure that the data is 16 bytes long. And so we definitely need a way to split the blocks up, split the data up into these 16-byte blocks or chunks. So let's make a function here called split blocks. And we take our data. Let's see, let's get the length of the data. And we're going to iterate over the range of 0 to the length divided by 16. And we're going to leave that as an integer. We're going to let it floor it. And we're just going to separate this 16 bytes at a time. And I times 16 to I plus 1 times 16. And then we'll return our blocks. Now, because my XOR function kind of expected, we expect it to return some byte array value, we might as well just cast our plain text as a byte array as well. So let's just say plain text equals byte array plain text. And then our plain text blocks will then become just the plain text split up using our split function. So that's pretty easy. So far so good. Nothing really complicated is going on here. We basically just prepared the data. But we're going to need to get ciphertext, and since we're getting our ciphertext 16 bytes at a time, this tells me we're going to need to aggregate all these blocks together somehow, and I'm just going to go ahead and make a variable to hold all this. So ciphertext blocks is just a slice, empty for now. Now the idea is again pretty simple. We're basically just chaining our input, so our output to our input basically. So for each block that we encrypt, we're going to just XOR our output with our plain text, our previous output with our plain text before we run it through the cipher. So ciphertext blocks dot append, And there is a gotcha that I didn't explain. And for the primitive that comes from PyCrypto, it expects a string versus a byte array. So we have to do some annoying casting to get it to work. But I mean, I'm not worried about the efficiency of the code at this point. For just what I'm showing, it's fine. So we want to append self.cipher .encrypt. This is the API. The string cast version of XOR ciphertext blocks I -1 actually, and we XOR it with our block that we're currently examining. So that's pretty much it. However, remember there was that thing that I said not to worry about. It was called the initialization vector. And the reason this comes in is what happens when we have our first plaintext block. You know, what do? We don't have any previous ciphertext to XOR with it. So this is where the initialization vector comes in. This will fill the gap where we don't have a previous ciphertext to XOR with our plaintext. And so a good IV should just be random-ish data, and the getRandomBytes function will be good enough. So IV for initialization vector is getRandomBytes, and since AES expects 16 bytes, we'll do 16 bytes of random data. Now, because of this, one thing is we need to handle that special case. So if we're doing the first block, in other words, if I is 0, we don't XOR the previous ciphertext block because now that doesn't make sense. Now we XOR the IV with our block and then append that to ciphertext blocks. Now, otherwise, if we're not on this I = 0 case, then we perform our normal encryption. But here's the thing. How do we, when we decrypt later on, how do we know what our IV was? We don't store it anywhere. So how do we know? Well, the initialization vector should be random, but it doesn't have to be private. It can be publicly shown. So what I'm going to do is just append it first to the ciphertext block so that when we decrypt, it'll be the very first 16 bytes of our ciphertext. And that's okay. That's not a problem. So we'll just append the IV as well. Again, because we're appending this, that means we have one extra move forward on our indexing. So for this other case, instead of I -1, it now becomes I. Hopefully that makes sense. But basically, we've inserted data twice here, and this IV shifts the index that we want for our previous ciphertext to just be I. Okay, cool. Now what we're going to do is we're going to concatenate all of our ciphertext, base 64 encode it, and then return it back. So we're going to return base 64.b64 code. It's just a random, not a random, just an empty string .join ciphertext blocks, and we're done. So this is our encrypt function, and it was very simple to make, and yeah, it only took 13 lines of code, including whitespace. So, however, does it work? So let's just say we initialize part of this here. AES CBC. We're going to let it create its own key, and ciphertext equals cipher dot encrypt, and let's just encrypt 16 A's. Whoops, too many A's. 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go, 16 A's. And we can print out the ciphertext. Whoop. I forgot that I imported XOR, or util, not XOR, so this should actually be util.xor and util.xor. I did say there was going to be mistakes. Cool. So now we actually get our data, and the reason it's much longer than just 16 bytes is, again, because we also have this initialization vector that we've prepended to our entire ciphertext, and this is so that when we decrypt, we can actually get this IV and use it to help us decrypt our message. So this is working. This is good. We have an encryption method. Now we need to do the reverse and get our message back. So let's go ahead and do that. Now we know our data is coming in and in the form of base 64 encoded string, so let's just go ahead and make sure that we base 64 decode it. So ciphertext equals base 64.b64 decode and our ciphertext. And, you know, again, let's just cast it as a byte array to make our lives easier. Okay, so now we need to get our ciphertext split up again into 16-byte blocks, and now we have a convenient function for this, so we just say ciphertext blocks equals self.splitBlocks and our ciphertext. Now already this is looking pretty much similar to the encryption, and that's good. You know, it's supposed to look that way. It's actually very intuitive, in my opinion. And again, it's very similar. So here we're going to also create a holding variable for our plaintext blocks as we decrypt them. Now we don't really worry about separating out our IV at this point. It's not necessary. We only stored the IV as a variable in the encryption just because we were initializing it as random bytes in the first place. But now we know it's in our ciphertext, so what we can do is just continue and go through our process of actually decrypting and just, you know, assume it's going to be there. So for I and block and enumerate our ciphertext blocks. For this one, we don't need to handle a special I equals 0 case. This one we can actually just say if I equals 0, continue. And the reason this is because the first block is going to be our initialization vector, and it's not encrypted. So there's no point in actually performing an encryption operation for the same reason, you know, that there was no reason to just encrypt the first byte of plain text alone. So in this case, we skip it because the reverse operation, we need to XOR our output of the decrypt function with the previous ciphertext, and we don't have anything previous to our IV, so we just skip that and continue on. Now, plain text blocks is going to be appended with. I almost screwed that up. Let's see. Append self dot XOR self dot cipher dot decrypt. And again, it expects a string, so we cast it as a string. String of our block, and then we XOR it with. Whoops. We XOR it with a previous ciphertext block. And just to make it easier to concatenate everything, we're also going to string cast this as well. Yep, pretty much it. And I'm missing a parentheses, so let's fix that. And we're done. And so that was it. To output our plain text again, we just do a string.join our plain text blocks. So again, this code is very simple, and this is technically a fully working CBC mode of operation block cipher, and we can actually test it by testing our main function. So return our ciphertext, and then now our plain text equals cipher.decrypt our ciphertext. And we can print out our plain text. And if it works correctly, and I'm screwing up again with the XOR, util.xor. And I forgot to return it. Okay, so after that little hiccup, you can see that we get our ciphertext, and when we send our ciphertext back through the decrypt function, we actually get our 16 A's back. And so this is pretty cool. It's a very small bit of code, but it works, and it was very quick to set this up. So there is a problem, and the problem is evident if I try to add something that's not a multiple of 16. So let's throw in a couple B's. Let's throw in 6 B's. Now, 22 bytes is definitely not a multiple of 16, so what's going to happen? Well, you can see that it actually truncated our output, and that's definitely not good. So when I said this was working, I should have clarified that it's actually not technically working, and it's technically working in the sense that if you're working with a multiple of 16 bytes of data, it's fine. But if you're not, then it's not working because it's just truncating your data, and that's not good. So the way we combat this is we end up adding some padding to the data. So there's many ways of adding padding. You could just pad it with random data. You can pad it with just all of one single byte value. However, there is a specification that's commonly used, and it comes from a standard called the Public Key Cryptography Standard number 5. PKCS number 5 for short, and the padding specification is actually pretty simple. I can actually show it to you right here. So if I have some data that I need to pad with, let's say I have my 6 B's, just to keep it consistent. Now I need to pad it with 10 bytes of other stuff. 4, 5, 6, 10. So these X's, we need to make it something. Now PKCS number 5 has a padding specification that says, you pad however many bytes you need to pad with, that's the byte value that you pad with. So in this case, we need to pad with 10 bytes, so we pad with a byte value of 10. Now, I'm not going to show a byte value of 10 by doing 10, 10, 10, 10. I'm just going to represent it as A in hexadecimal form. So this is kind of wonky. Just pretend that the capital A is hexadecimal. I know it doesn't really work because B is ASCII and capital A is not. Okay, it's not by ASCII value 10. So just bear with me here. Just realized how stupid that looks. You know what, just for this, let's make it numbers. That way I can do it in hexadecimal, it's not confusing. So yeah, so here's what we're padding with, and likewise, if it was reversed and we had 10 ones, then the byte value we pad with is 6. We need to pad 6 bytes, and the value of those bytes is 6. And so that's PKCS 5's specification for padding. This is actually pretty simple to set up, and this is also going to be what I'm going to intentionally muck up just to leave the vulnerability open for the padding attack when I do the next video. So how to implement this in our object here so that we can encrypt data that's not perfect 16-byte multiples. Multiples of 16 bytes. Okay, so for adding padding, at least, it's pretty simple. So I'm going to create a private function here, private class member. So add padding. and we're going to input data, and I'm also going to return data. I'm going to assume that the data is immutable, so we return data. All right, so right off the bat, we know that padding is going to be equal to 16 minus whatever the length of data is, modulo 16. The reason we have to do the modulo function is because otherwise we would be limited to 16 if we just did, simple subtraction. And so the modulo just helps get the remainder. And it works because when the length of data is a perfect multiple, that's the other thing I forgot to say. But anyway, there's another specification that says when you have nothing to pad with, just to make sure that you're able to remove the padding later, you add padding anyway. And I apologize, I was supposed to say that, but again, the camera, I'm not familiar with doing this, and I apologize. So anyway, if the length of data is a perfect multiple of 16, then this becomes 0. This length of data modulo 16 becomes 0. 16 minus 0 is what you pad with. This is the way it works. You want to pad with what you want to pad no matter what. That way you don't run into a case where if I have 16 ones, is that 16? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. If I have 16 ones and it's a perfect multiple of 16, if I later want to strip this padding, I'm probably going to want to examine the last byte. Well, I'll see this and say, oh, well, I have 1 byte of padding. I must, have to remove that, and I'll end up truncating my data. So I apologize. I was supposed to say that, and I forgot. Forgive me. So anyway, that's why when the length of data is a perfect multiple of 16, we want the padding to be 16 anyway. And I probably just totally confused everyone, but I apologize. I'll get better, I promise. So, okay, so we have our expected padding that we want to add. The way we add it, well, we can assume, again, that we're working with a byte array instead of a string. And we can say that, we return data plus byte array of padding for nothing in a range of padding. And this will give us what we want. And let's go ahead and add this. Let's say our plain text is now on encryption. This add padding to our byte array of plain text. Okay, so right off the bat, we're just going to add the padding to our plain text, and then we go through the process of splitting it up, which now all of our blocks should be 16-byte multiples. Okay. Now, when I run this, now we should at least get our B's back. However, we'll also probably get some new line characters. We're padding, in this case, we are needing to pad with 10 bytes of value 10, and since 10 is the value for new line, we're going to get 10 new line characters after our B's, or we should if this is working. And it is, so you can see pretty clearly we get those new line characters. Okay, now the problem becomes we need to be able to decrypt and strip that. We don't want the padding to be shown. The user doesn't actually care, or whoever is using this doesn't care about the extra padding. In fact, it can really mess them up if they expect their data to be returned only and not some junk at the end. So we need to remove this. And again, we remove it just by checking the last byte of our decrypted ciphertext, and we check the last byte, and that should give us the padding that it has, and then we just remove all of that padding. And actually, this is where we're going to introduce the vulnerability that leaves us open to the padding oracle attacks. So this is the this is really the crux of the vulnerability. Okay, so in this case, we already have our plain text, and we're going to strip it from our plain text, and we're just going to use another function that we make called check and strip padding. Okay, and in this case, I'm going to, since we're working with a string in this case, we've already, like I said, we've cast all this stuff as a string just for convenience. But now this function is going to be used after we do that, so let's just cast our data. The idea is we're going to join our data together, and what we would normally just return, we're going to run it through this check and strip padding function first. Okay, so check and strip padding, our data is now equal to byte array data. So now our expected padding is now going to be the last byte, the value of that last byte, which is just data index -1 in Python, which this is one of the reasons I like Python. I don't like it sometimes, and I like it sometimes. This is one of the times I like it. It's very nice to just get the last element. So we just do data -1. That'll give us the value, the byte value that we expect. And we're going to just do if for byte in our data from length of data minus expected padding. If the byte is not equal to the expected padding, then we know something's wrong, and let's raise a value error. All right. Otherwise, we're going to just return the data. We're going to actually string cast it just so that we give back what we get in. And we're going to string cast data all the way up until the length of expected padding. Oops, the length of data minus the expected padding. And so this should work. And again, we're going to add this right at the end here. Self.check and strip padding. Cool. Now it should strip the extra bytes, and we should just get our A's and our B's and nothing else. Yeah. So I've made a mistake. Oh yeah, I was supposed to do a slice, not an actual value. There we go. And oh, I actually have to add a -1 here. No, I had it right. Okay, I was second guessing myself and I was wrong. Okay. So now we can have our plain text in multiples of whatever we want, really. Even if it's just under the byte multiple, we should get it back. And we do. We get back what we put in. And this is what we ultimately wanted. However, the fact that we raise this value error is ultimately the vulnerability that we've introduced into our system. And so this is what's going to allow attackers to use the Oracle attack, the padding Oracle attack, to be able to decrypt any message just by exploiting this. It's really cool. And again, I don't want to spend too much time on one video, so I just wanted to show how easy it was to set up CBC and again, just how subtle this vulnerability is. I mean, this is something where most people would say, well, if we don't get the right padding, we should raise an error. This is what a lot of people will think, and it's intuitive, right? You know, you want to alert the user that, hey, you gave me some bad input, and unfortunately, this is where you leave yourself open to an attack, because anytime you leak information about a system, then it allows an attacker to use this to his advantage, and this definitely gives a big advantage to the attacker. and again, we'll see that in the next video, part 2, where I actually go through creating the padding oracle attack, and you'll see just, you'll see the data that's encrypted just get completely encrypted in a way that is so easy that you'll just be hitting your head like, wow, this is just dumb. But anyway, I hope that the video was cool, and that it explained things a little better than a long blog post, and I hope the next video is helpful as well. So I'll see you in the next video.